Thank you. Thank you so much. Now we need to try to make the tech work. I'm going to get it. I just need to find where the screen is. Here it is. Here we are. Sorted. Great. Thank you so much. Very happy to be here. I'm a bit, I need to disclose something. I've never actually run a pipeline in Nextflow. I feel very bad about that. So I feel like a massive fraud here, basically. That's the baseline. And I'm going to talk a little bit about Nextflow. Actually, not a lot, but I'm hoping that a lot of what I'm going to include will kind of resonate. And if not, well, we can all go for a drink early. Okay, so being here, I don't need to convince you that computing is great. I always start with that because I'm not coming here saying we shouldn't do compute anymore. Geraldine mentioned it, like my background is in computational science. That's what I do. I would be out of a job. So I just cherry-picked some examples. What's interesting is it also helps us to fight climate change. Again, cherry-pick examples, lots of great applications of AI, but not only, computing technology in general to optimize energy grid and so on. So that's the good side of it. The problem is the carbon footprint of science. It's really hard to understand what the carbon footprint of science is. There are lots of estimates. Usually we find numbers for scientists between 4 and 40 tons per year. For context, the IPCC target for keeping global warming under control is around 2 tons per year and per person. So we're already over that. Now, in biology, if we focus on that, Emble published a report last year that was really interesting. They calculated the overall carbon footprint, and they did some interesting calculation. They found that it was around 65 tons of CO2 equivalent to publish a paper out of Emble. And around 29 tons per full-time staff. That includes both wet lab and dry lab research. So it's not all computing, but still, it's quite big numbers, right? If we compare it again to the 2 tons, we're a little bit higher than that. But computing is the green option, we know that. So let's look at data centers. Again, so much uncertainty here, but just a rough number, around 126 megaton of CO2 equivalent per year, which is the global carbon footprint of data centers. That's the same as the entire American commercial aviation. And, you know, lots of planes over there. Okay, so data centers do a lot of things, but, you know, science is just one of the small things they do, so maybe that's all exaggerated. And that's where it gets interesting, and that's really how I got into this topic. Because, you know, people have been working on optimizing data centers for a long time and doing really excellent work on infrastructures and hardware. But the problem didn't really reach scientists. So actually, before we go there, a quick question. How many of you have looked into the carbon footprint of the research you do? By like quick show of hand, if you have? So got maybe 10, 20 at a push? Okay, no, but that's, I mean, that makes sense. And that's really why we started on that, is because it's not something that gets brought up commonly. And when it does, it used to be really hard to do. So I really can't blame you for not doing it. So we started looking at some applications, and we said, okay, well, we're a group of geneticists, and we thought, let's do genome-wide association studies. If you're not familiar with it, it doesn't matter. Let's look at 1,000 different traits in UK Biobank, and let's use maybe not the best way to do it and not the best software, but something that is commonly done. And we get a carbon footprint that's equivalent to me flying to Paris from London for breakfast every morning for 6 months. I would love to do that. I really miss French pastries, but probably not best for anything really. It doesn't mean everything has to be that bad. Let's look at a pipeline that, you know, you can see in brackets. The just computing resources are a little bit smaller, and we're talking kilograms, and we can go elsewhere, and then suddenly we're talking grams. The idea of this slide is to say we don't need to get completely paranoid about everything we do in a computer. But the fact that some of the analysis we do have disproportionately high carbon footprints means that we need to be mindful about these. Okay, it's all about AIs these days, so let's have a look at that. There's this paper that compared a few of the large language models' carbon footprint. The top one, GPT-3, you know, is kind of the ancestor of ChatGPT, and training the model once was around 550 tons of CO2, and that's, you know, without the research or anything, just to train the model once. And then we had 3 point something else, and then we had 4 and 4.1, and it seems there's a new version every week these days. So that's part of the problem. And just because I couldn't resist it, let's combine AI and biology. So looking at AlphaFold, this is completely unscientific in a way. It's completely back-of-the-envelope calculation based on the original first AlphaFold publications, and we find that training it is around 4 tons. So we're like, okay, well, I mean, considering the applications and the potential for it, that's not a bad deal. Obviously, AlphaFold is not the only one. Meta had their own language model reapplied. And in their publication, they said we need to show that we can predict on a lot of sequences. So they applied it to 600 million. Suddenly, we're reaching 100 tons of CO2 for that paper, which is fine if those 600 million sequences are reused. If they're not, it's slightly less useful. It's an expensive publication. And there's another problem, which is in wet lab research, if you waste chemicals and reagents, it's really expensive, so you tend not to do it. For us, unless you do cloud providers and then you have a very direct cost, if you are lucky enough to be in a reasonably well-funded research institute and you can use institutional data center, it basically costs nothing to run compute. I mean, there is a cost somewhere, but it's quite low, and it's rarely the limiting factor unless you're working on enormous models. It's quite rare to hear, oh, we're not going to run that compute because it just takes too much time. It's just too expensive. Usually it takes too much time before it becomes too expensive. And anything that is free is tempting to waste it, and there's less incentive to be efficient about it. It's particularly a problem somewhere like here, where most of us works in bioinformatics or health science in general. And I mean, I'm in the Department of Public Health at Cambridge in the cardiovascular epidemiology unit. Half our units work at the intersection of health and climate change. So I feel a little bit bad where we kind of burn a lot of carbon to try to tackle the problem. It's a bit of a bad circle to be in. So we just think, well, it doesn't mean we shouldn't do the research we do anymore, but we should at least be mindful of that. Okay, before diving straight into the compute side, if we take a step back and we think about the different ways research impact the environment, we've got these 4 main categories, right? We've got travels, we've got wet lab or physics lab, I guess, related impacts, we've got computing, and then we've got just general operating offices. And so I'm mindful that it's even worse than Geraldine earlier. I'm between you and the end of the day, which is probably the worst part to be in. So I'm not going to go over all of that, and I'm going to dive straight into computing. And I'm not going to talk about things like Zoom or emails, but we can have a chat about that later. But really, just focusing on what you're all doing here. One of the really good changes over the past 4 years or so has been how many more fields have been starting to tackle this issue. This slide about past work used to be really quick. They used to have the 2 top left papers, and that was about it, really. Made the lit review for my PhD very easy. But other than that, it's really good to see things like neuroscience or physics or geography, and a lot of fields just saying, okay, well, let's look at the carbon footprint of what we're doing. Because having this field expertise is the best tool possible. And there will be a theme, and basically, I'll just end up by giving you a lot of homeworks on things you can do. It's all the same, just in terms of how you think about your compute. If you just have super powered gaming computer, or you use virtual machines, or you use cloud or whatever, the principles of what I'm going to talk about are roughly similar. Okay, so if we dive in, one of the reasons this topic is quite complicated is there are so many aspects to consider and so many ways to slice that pie. We can start with the first one. So we can think about use stage impact. So that's carbon footprint from using electricity to power the computer, and that's usually what we think about. But we also need to think of embodied impact, which is manufacturing, distributing the hardware, disposing of it at the end of its lifetime. If we look at consumer devices, that's your phone, your laptop, your tablet, between 70 and 95% of their total carbon footprint is just from manufacturing. Which means for this equipment, what you do with them is not very important. What matters is keeping the equipment for longer and not replacing them as often. The manufacturing share for data center hardware is a little bit lower, not so much because they're better to manufacture, but just because they get used so much more in the long run. If we look at the other end of the spectrum and we look at electronic waste, we've got this quite depressing report from the World Health Organization highlighting that there's up to 80% of the 50 million tons of electronic waste are handled by what they call informal waste workers, which basically mean dump sites, and you can imagine all the health consequences coming with electronic hardwares, including a lot of children and unexpected raises. And so that's quite an interesting, well, that's quite something we need to keep in mind. On this note, let's look at carbon footprint. I've been talking about carbon footprint mostly, so greenhouse gas emissions mostly. And that's fine. That's really something that's a metric people are getting familiar with, so it's a really good tool to use. We still need to think about broader environmental impact, water usage, land use, rare metals extractions, and so on. There was this report in Nature a few years ago. I have no idea how much water an average size hospital uses, but I'm pretty much sure it shouldn't be like, you know, the unit to compare a hospital, a data center to. That's not a great comparison, but it is a problem, and we've seen lots of examples, for example, in Chile, where some cloud providers had to back out from building data centers because the people there had just said, well, we don't have enough water for ourselves, so please don't bring a very water-demanding building in here. And you know, Ireland has similar issues with electricity usage and so on. So it is starting to be a real problem. This is a not very neat plot, and you don't need to look at all of it, but if you look at the categories on the left, sorry, if I move it's not great. If you look at the categories on the left here, these are all the standardized way to think about environmental impact of products. And climate change in the middle is the only one that is greenhouse gas emission or carbon footprint, basically. And you see that's just one amongst many. So some of them are quite self-explanatory. If you look at the bottom, you've got land use or resource use in terms of metal, which is very relevant for electronic hardware and so on. And so that just shows the complexity of the problem. And what they try to do here is on the right-hand side, you've got planetary boundaries. So, you know, the kind of boundaries if we wanted to leave the Earth in in as good a state at the end of the year as we found it at the start, which we exceed in many categories. So they kind of try to do a bit of a mapping exercise. But the point of that is just to say, there are so many more levels we need to be mindful of. And sometimes something that reduces greenhouse gas emissions might not be great if actually the trade-off is to increase impacts in other categories. Another way to think of it is it's not all about compute. I mean, especially in bioinformatics, I mean, it may be an unpopular thing to say here, but sometimes compute is a very small part of the process. You know, it's all about the data, and some researchers will do very little compute, but they will generate enormous amount of data, and they will leave other people to do the compute. If we look at an average data center, so optimized one can be a bit better, but average data center, only half the power you provide to the facility actually powers the servers. Then it's 10% for storage, and the remaining is overheads, which is mostly cooling. Now, storage is complicated. It depends on a lot of factors. If you just want a quick rule of thumb, if you have some kind of amount of data in mind now, the order of magnitude is around 10 kilograms of CO2 equivalent to store 1 terabyte of data for a year. But again, it can vary greatly on that. If we think about the computing itself, this is actually not that hard to estimate, and that was one of the surprises when I started working on that. There was the lack of tools and the lack of resources for people to do it, but actually the basic principles are quite straightforward. We need to figure out how much energy we need, and that depends on the hardware and the software, what we're doing on what machine. And then when we know how much energy we need to figure out the carbon footprint of producing that much electricity, which mostly depends on where you are in the world, because most data centers are plugged into the main power grid. And so we've got this electricity map, which is really interesting. They show a real time, so the map changes all the time, and it's basically the carbon intensity per country. You can see, and that's the biggest difference actually between locations. Let's look at a few examples. So focusing on Europe, let's say you decide to move your compute from Sweden to Poland. You multiply your carbon footprint by 46 on average. Same hardware, same software, same everything else, just because the electricity is more renewable in Sweden and more powered by gas and coal in Poland. Okay, but that's a bit extreme, moving your compute between countries like that. Let's focus on the West Coast in the US. So we're in Washington State, and we just moved between 2 different counties. Suddenly, we multiply carbon footprint by 9, because again, the energy providers are not the same, and therefore the share of renewable is not the same. So that's a little bit scary. But it shows that there is great opportunity because we are quite lucky in terms of research that you don't have to be next to your servers. You know, wet lab people can't do that. They have to be next to their equipment. So that means we do have a lot of opportunities to leverage renewable energy. Okay, after all this doom and gloom, I always feel I need to have this slide in here. I'm not at all saying we shouldn't do science, and actually there are a lot of situations, and Nextflow is a great example of that actually, where doing better science in a better way also comes with greener consequences. So you know, a lot of things in Nextflow is all about reusing containers and reusing pre-run code so you don't have to rerun all the pipeline. Well, that's brilliant. It means you don't actually waste compute too much. And that's better practice. It means your code is more reusable. It means people don't have to, you know, reinvent the wheel every time. So all of that is great and also comes with sustainability benefits. So that's why it's so exciting actually to be here today, because it's really, Nextflow really has a great role to play in all that. So what we've been trying, so we called that initially the Green Algorithm Initiative. And it took a lot of aspects, but the original goal was really to bridge the gap between all the great effort in sustainability on the hardware side or data center side and scientists. So that scientists or researchers or people on the ground actually feel engaged with this topic. Because it wasn't really the case. And so part of this was building tools for carbon footprint estimations, and I'll show you some. Then taking a step back, and I'll show some principles. But then more recently, we got into community building and also some policy work engaging with the European funders. One of the big questions we have is measuring or estimating. So basically, there are two ways. You can try to measure what you're doing. So you plug a watt meter at the back of your computer and you see how much energy you're using. Obviously not very scalable, and it assumes you have control to the computer, but very accurate. Or can you estimate it completely from a user point of view? So assuming you have no control over the machine, you don't really know what's there, you have some basic information. And that's what we've been focusing on, again, to empower researchers to do it. I'm not going to go into great details, but just roughly, that's how you can estimate it. So to estimate the energy usage, you need to figure out how much power is being drawn, and you can focus on the processors, so CPU or GPU, and the memory, quite important. You include runtime, and then you include this PUE, which is this power usage effectiveness. That's a measure of overheads of the data center, basically. That's a way to include overheads. So it's total electricity provided to the data center divided by electricity that actually goes to the server. So it has to be greater than 1, obviously. And that's a way, to measure cooling. So closer to 1, the better. And now, there are lots of ways to do it in practice. If you're interested, we put out this primer last year, which is quite a short way and summary, just because of I won't be going into too many details. But roughly, there are 3 different ways of doing it. You can either use online calculators. You know, it's the same as the flight calculators, where you can go and you put, I'm flying from Boston to Barcelona, what's the carbon footprint of that? You can have packages in your code. So, you know, if you're writing Python code, you can just have a package in that runs at the same time as you're running, and it will track it in the background. Or you can have some tools embedded on the server or the whatever platform you're using that sends back information. So the packages is what is quite popular because it's a little bit easier to develop. The problem is they're all in Python. I mean, it's great for Python users, slightly less so if you're not a Python user. And they work mostly for AI. Again, good if you do AI or machine learning, but if you don't, slightly less practical. And that's really what motivated us. So that's the first tool we released. We released it early 2020. And the idea was to have this online calculator where you just go on there, you say, my model runs for that long. This is the kind of hardware I have. This is where I'm in the world. Here's my, and it gives a rough estimates of carbon footprint. So it's all open source, it's all on GitHub, which I found out that putting all your data on GitHub is the best way to make sure no one will ever dig into your data. That's very successful. And that works great, and you know, it's all on there. If you want to check it out and have fun with it, it's been quite popular. Obviously, the problem is you're having 100 different runs. They all have slightly different parameters. It's not very practical to start uploading everything on the calculator. And I was halfway through writing my PhD thesis, and I really didn't want to, so instead I decided to do something else. And basically the idea was to say, well, okay, I'm using a Slurm-powered data center, so that's the workload manager. And everything I do gets logged because I said it's free, but actually my lab gets charged just a little bit of money for it. So could I pull all the logs and based on the logs use the online calculator, but automatically, basically, on every log? It turns out it's reasonably straightforward to do. And so I did that, so we called it Green Algorithms for HPC. And it used to give this slightly less pretty output, but a lot more informative. It gives information that I wished I ignored, like the impact of failed jobs. That's depressing. Or also memory of allocation. So it all looks very good here, but that's because I actually haven't been doing any compute, so that's cheating. But basically, that's the kind of output. And importantly, it doesn't need any admin access or anything. So people can just run it. It's a very simple bash script. And now we've been working on that with other people, and now there's a prettier output, so you can also get the nice HTML version for people who don't like the command line. If you're interested in that, do check it out. And the next step is to make it a proper dashboard where it can be fully embedded onto the platform. Again, having this open access, open source dashboard for institutions that don't have existing tools like that. So working with people from EBI who've done brilliant work in this space. Time for the Nextflow plugin, but that's really exciting because everything we've talked about, some of you have probably been thinking, oh wait, well Nextflow is logging all this information as we go, and so you can actually estimate carbon footprint. And yes, very smart people have thought of that before, and they've been building this NF-CO2 footprint. It's really great. It basically does that. It gives you an expected carbon footprint at the end. I'm not going to go into too many details because there's a brilliant poster in one of the poster rooms about that. So I would really encourage you to go check it out and test the plugin. I think it's in beta version still, but yeah, it works. Do check it out. And in terms of homeworks, we talked about people on the ground having the best expertise to actually estimate the carbon footprint of their work. Well, now everyone in this room can do it very easily. And that would be very cool if, I don't know, maybe next year at the summit, we can come back and say, this is an overview of the carbon footprint of bioinformatics 2.0. That could be a cool thing. If you are even more keen on that project, they're also recruiting a Nextflow developer to work on this plugin and some very cool project at Tübingen. So Sabrina is somewhere in the room, and so if you catch her, do have a chat, and if you're interested, strongly encourage you to apply for that. Now, we said estimation is all great. We're all doing it, and people use them. Does it actually work? And people at Google were not very happy with us. You've done something right as a PhD student when you get Google, AI team dumping on you on Twitter. That was quite an interesting time. Anyway, they said, no, carbon footprint of AI is not a thing. Please stop saying. So they tested our calculator to show that we were crazy people. Basically, our tool is the green bars. And what they wanted to show, it's the ratio between estimate and real value. So you want all the bars to be as close to 1 as possible. OK, let's start being positive, because I'm the one giving the talk, so I can decide. Let's look at the one in blue here. We are incredibly close. I mean, if you had told me my calculator was off by 20%, I would have been like, that's fine. It's an online calculator made to give a rough estimate. I'm happy. We are within 9% of the real value. Like this one on the right, we're 2% of the real value for something that's based off no measurement, just runtime and usage factor. So it works incredibly well. Obviously, that's not what Google wanted to highlight. This is the bit we had to be scared about. And they said, look at this calculator. It overestimates carbon footprint by a factor 2.4. First, same order of magnitude. I was actually happy with that. I mean, I'm fine. But let's try to understand what happened here and why we're doing well in some cases and not so well in other cases. If we look here, the ones we're doing bad at are using Google's TPUs. So if you're not familiar, these are Google's very own AI GPUs, basically. They call them TPUs, but they're GPUs of slightly different. They are the very own. They don't sell them. What everyone else does is when they sell a chip, like NVIDIA, they have to tell you how much power you need to give to your chip. So you have an expected power usage. It's a metric called TDP for thermal design power. As a side effect, it also means that you know how much cooling it needs, so you don't burn down your house, all benefits. Google doesn't sell their TPUs, so they don't have to tell anyone about power usage, and therefore our calculator was basically working off rough estimates, leaked values, which were quite inaccurate. So the conclusion of that graph is when manufacturers are transparent, estimation works incredibly well. When manufacturers are not transparent, estimation doesn't work. I'm happy with that. Apparently they realized it didn't show what they wanted because the graph actually disappeared for subsequent versions of the paper, but archive's memory is eternal. Okay, let's look at slightly more serious benchmark. This is a very good team in France which did all the similar work here and compared estimates from that. Again, let's be positive first. If you look at where the arrow is pointing, so GA is green algorithm, the other ones are other tools, all very brilliant. The first conclusion is all the tools work. I mean, we can try to say one is better, but realistically, they're all giving good estimates. GA is giving the best one though. Just saying. But it doesn't really matter. Realistically, it's all the same. And GPU benchmark, it worked brilliantly well. Now, we have to be honest and look at the top row here. It doesn't work so well for CPU. We tend to underestimate, estimate only a third of the real energy usage. And the reason is quite simple. A GPU, especially in an AI benchmark, is quite predictable. You put it, it goes 100%, it runs 100% until it's done, then it's done. CPUs, it's the Far West. We don't really understand what happens there. But that's something we keep working on, and hopefully we can make some progress on that. But that's really something we need to improve. Okay, frameworks. Well, after working on that for a while, we took a step back and we said, let's put together some principles for the field. Greener principles for computational science. So we came up with these ideas. I'm not going to go through everything. But the idea was to have some basic principles for computational science moving forward. The first two, governance and responsibility, was who has a role to play. And the answer to that is quite predictably everyone. But really, it is a real everyone. We need both grassroots movements in sustainability, but we also need top-down approaches. So anyone who is interested can really help with that. We need to engage with industry as well. I mean, an example with EBI and the AlphaFold database, I could have, Nextflow is another example. There are a lot of examples where research institutes, just by promoting better science, actually promote reproducibility, but also sustainability. In the UK, just recently, we had this Concordat for environmental sustainability, which is quite nice. It's basically large funders and large organizations who came together and said, oh, okay, we do actually have a responsibility to conduct research in a sustainable way. So that has been quite exciting. And just last week, I'm really excited about this piece, partly because I was involved in it. So that's the first time European funders came together and many of them endorsed a document saying we have to move faster and we have to be stronger about how we embed sustainability in how we do research. So you'll recognize maybe some funders from where you're from, but a lot of national funders from different countries came together on that, and that was really exciting. So driven by EMBO. I'm not going to go through the different principles. The text is as you would expect it, but the fact that it was endorsed so strongly is the really exciting part. Another thing we've been trying to push for is environmental impact statement, just saying in grant application, people should be able to justify the carbon footprint of their work. And why it's worth it. We do it with money, we do it with ethics already, so we could do it with sustainability. And there's this interesting example that came out of France where they just decided to do it. So basically they decided to embed this environmental impact statement in their AI funding calls coming out of the National AI Fund. And they said, it was nice that they got in touch, and they said, all the applications have to use our online calculator because then it makes it comparable. Maybe everyone's wrong, but at least everyone's wrong the same way. And so we've been working with them on that, and the real good news is it just worked. There wasn't a big backlash, people understood why they were doing it, and so that has been a really, really interesting application. So many brilliant efforts coming out of industry. A lot of the innovation on how to make data centers more efficient has come out of industry. I really like the Microsoft project of putting data centers underwater. It actually worked reasonably well. And so yeah, the Lumi data center is quite interesting. So a lot of that. What we have, and as you've probably seen with the Google example earlier, is there's a little bit more convincing to do. And that has to do with just some people who don't believe in all that. So we have some examples here from both Google and Meta who just say that the carbon footprint of compute and AI is BS and just doesn't exist. Which I feel a little bit smug now that the latest sustainability reports have been released. And so I have a little bit of a I told you so moment, where both Microsoft and Google actually showed outstanding emissions increase over a 3 or 4 years period. That's massive considering the target was net zero very quickly. And Google actually acknowledging that AI is putting their sustainability targets off track. So we'll see where that goes. Estimation, I've talked a lot about that. I'm not going to go over that again. Reporting, that's something we've been trying to do in our group and more people have been trying to do, is just to, at the end of our publication, we just acknowledge the carbon footprint of the work presented and as a way to raise awareness. And that's been quite interesting to do. I mentioned earlier, so a few years ago, that's where we started from. We wanted to look at the carbon footprint of the work we do because we're a bioinformatics lab. And then we realized there was no tools, and then we started building the tools first, and this small project ended up slightly bigger than planned. I'm not going to go into the details here. The thing is, it's 3 years old. We started working on that 4 years ago. And also, we had to work off the data that was already in public benchmarks because we didn't want to rerun the analysis to tell people about the carbon footprint of running analysis. I mean, the irony was a little bit too much, which means we were limited in the tools we could benchmark. We were limited in the information we had. We had to make assumptions. And that's why I mentioned earlier, doing a V2 of that paper using all the expertise we have, for example, in this room, around Nextflow, using, for example, the Nextflow plugin would be absolutely brilliant. So if you're interested in any of that, do get in touch. That'd be very cool. What can we do to reduce it? I'm not going to go into details on that, just because that's everything I've been talking about here, already. But if you're interested, it's a very small 10 simple rules on this topic. And I'll just highlight the example of neuroscience as a great example of what people can do by diving into their field. So this is an example of neuroscientists who decided to tackle the carbon footprint of their work. So they had the field expertise on that, and they tackled some of the tools that are commonly used there. This pie chart is depressing. The total pie is all the data being generated by the brain MRI pre-processing software. The green bit is what is ever being used by anyone. And all the data just gets generated because of the default options, basically, and has no reason to be stored. And then the data gets stored for decades because no one dare deleting any data. Maybe rightfully so, but still. And so they came up with very concrete examples and very concrete recommendations to really reduce the carbon footprint of this kind of analysis, which is really cool. Something else that came out of the SSI is CATS. So working with other colleagues, but they're doing all the hard work, is this carbon scheduler. So saying, okay, well, can we run our compute at the time where most renewable energy is available? And in the UK, we've got a little piece of software that tells you in the next 48 hours what is the carbon footprint, for carbon intensity for each 30-minute window. So you can say, okay, well, what's the best window in the next 2 days to run my code? Because we all have code that we don't actually need now. We're fine to have the code in like 1 day, or it doesn't really matter when it runs exactly. So that's a little bit of an ongoing project that's been quite fun. I mentioned cloud computing, and we mentioned, for example, the opportunity of choosing location. That's something you can do with cloud computing that maybe you can't do otherwise. That's a great reason to use it. The data centers do tend to be quite energy efficient. Couple of caveats that it's important to be aware of. They tend to advertise power usage effectiveness incredibly low, which is true sometimes, but it's not always true for the particular data center you're using. So there is some progress on that, but you need to be a bit careful about that. And all the carbon neutrality claims rely on carbon offsetting, which is basically worthless, sadly. There was this study by journalists recently that studied one of the recognized carbon offsetting providers, and they showed basically that 90% of the carbon offsetting credits sold had no benefit for the environment whatsoever, despite, in theory, they were supposed to check everything. So that's a little bit sad, but something to be mindful of. Okay, and then education and research. That's pretty self-explanatory. We need to train people and to educate it, and research, because I've highlighted everything that can still go wrong, so we need to better understand what's happening there. And the final part in the original greener principles, if you remember, is cultural change. And why do we need it? Well, one of the reasons is rebound effect. You make a pipeline, you make a tool, you make something to be 10 times more energy efficient. The main result is everyone uses it 100 times more. That's great for innovation, that's great for science, slightly less good if your goal was to reduce energy usage in the first place. And so that's why we also need to work with researchers and scientists on the ground. Part of that is to build a community. And because there is so many people who are interested in this topic, it doesn't mean it's the focus of their work. It just means that they happen to do bioinformatics, astrophysics, whatever, but also want to think about the sustainability. And there wasn't really a place for them to connect. So we've been trying to build some of these initiatives. We're going to be ramping it up over the next few months. But one of the places that is already online is this online forum. So it's very straightforward. It's just a place. It's quite low-key at the moment, but if you're interested, go on there. And it's just a place for people to ask questions, to connect, to share resources, and hopefully that can be useful. And I'll finish by talking about Green Disk. Well, finish a bit. I still have a few slides. But certification schemes can be incredibly useful. If any of you do wet lab research, you may know of things like LEAF or My Green Lab, which are these sustainability schemes. It's a great way to provide a roadmap for groups on how to be more sustainable. Unfortunately, there was nothing for computing, and that was a really big gap. So we decided it needed to be done. So we partnered with the Software Sustainability Institute in the UK to build Green Disk. So what is Green Disk? It's a certification scheme, and so it provides a roadmap for group and institutions, so both, to first understand and then reduce the environmental impact of the computing-related research. As most of these certification schemes, you can get a bronze, silver, or gold certification, depending how far along you go. It applies to both group and central teams. We did a few things that are completely novel. You would maybe not believe it. We made it free and open access, which, as far as I know, is the first sustainability certification scheme that is. Which is a bit of a surprise, because why put that behind a paywall? If people just want to do the things and not enroll in the scheme, I'm fine with that. The more work, the better. Part of that will mean it's very much community-driven. And yes, the first version, so we actually just released that before the summer in June. The first version probably won't be perfect, and the second version will be very different from that. We had piloted the first version, so we're hoping it won't be completely wrong. But yeah, it will change a lot over time, and that's one of the benefits of being open access as well. Just to give you a flavor of the bronze criteria of the kind of thing we do, the bronze is quite easy. It's mostly inventories. It's understanding what are the big demanding pipelines, what are the big the big components, understanding what compute you use. Lots of people have no idea where is the data center they're using all the time, and also what happened to hardware, how much hardware we have, and so on. So it's mostly doing inventories. A bit boring, but really important first step. And then silver, you start to have to make change, which is a little bit harder. The idea of that is to have these two levels, so it can either be done by research groups or be done by central sustainability teams or IT teams. And in an ideal situation, in your institutions, both of them will work hand in hand and support each other, but it can also be done separately. If you're interested in that, it's very straightforward. You go on the Green Disk website. You should find it reasonably easily, but if not, let me know. And then you get started and you enroll, and then when we get to you, because we have to build up capacity, because the problem of free and open access is there's actually no funds coming in it, but hopefully funders will come through. And the community I talked about before is so important for that, because that's a natural place where people can share resources, share knowledge, share tips, and I really hope that's going to support it. And the SSI and people at the SSI have been absolutely brilliant on that. Okay, so the clock is starting to flash red, but I still have some time. Just some final thoughts. Actually, I'm going to wrap up on that. Really what I'm talking about here is cost and benefit. Is saying, I'm not saying we shouldn't do science, but before starting a project, we should think, is it really worth that much carbon? The same way that you ask, is it really worth that much money if you have a very expensive project to run? And I quite like the way the Royal Society in the UK put it. So they say, digital technology developed and deployed, they say in pursuit of net zero, actually I'd remove that, must be energy proportionate. So, there must be a reasonable expectation that they will bring benefits to society that will outweigh their own emissions. Now, it's very vague. It has to be vague on purpose. But we're already doing this kind of work with money, I said, or we do it if you do clinical research, you know that, for example, if you run a clinical trial, some patients will be worse off by taking part in the trial. But the argument is to say it will be, better for society globally, but you have to make a case for it. And so we can actually do the same thing for sustainability. This cost-benefit gets slightly more tricky when we think that it's not the same people who will most of the time reap the benefits and bear the costs of that. Because the population who suffers the most from climate change are not necessarily the ones who will benefit the most from the latest MRI technology or the latest smart speaker. So I don't have a solution there, just something to keep in mind. So if you're interested on the Green Algorithm website, there are all the resources. And very excitingly, we are recruiting. So we're going to be recruiting for a lot of roles starting very soon. So the advert is not quite out yet, but it's going to be out in the next few weeks. So we're recruiting for some research roles for working basically on every aspect I talked about today. Also a software engineer, and also some community engagement and project coordination. So if you're interested by any of that, well, I'm here until Friday, so do catch me, or very happy to, you can just email me. That would be great. Great, and I'll finish with some acknowledgements. Millions of people to say thank you, and I think we have a little bit of time for questions.